Hi friends, welcome you all to the 24th session of ARM-based development. So today we are changing the topic, not that I am going away from cluster architecture, but we are going to see something different from what we have seen so far. So what did we see so far? Let me summarize, okay, so that you know where we are. So this is a typical system, okay, system on a chip. We got a ARM IP, okay, inside that thing. So these are the connections, okay. We saw what does ARM do and what is the pipeline structure is, and then all the ARM instructions including the thumb state instructions, and then we saw how interrupts are handled, okay. The interrupts can come from outside world or it could be some of the peripherals in the chip inside, okay, doesn't matter. Now after looking at all the interrupt handling and exception handling, we started looking at coprocessor, okay. In general, how a coprocessor gets interfaced with the ARM processor, okay, and then we saw what are the coprocessor instructions are, and then we took an example how a vector floating point coprocessor is implemented as a coprocessor to the ARM core. Having seen all this, now we are going to explore some other different world, which is also part of the, maybe if I okay, one second, this is memory controller, maybe I should write it like that, okay. Now we are going to see, we are going to come out of the SOC, okay, and then going to see what all different kinds of memories, okay, how does help in achieving our goals of using the processor. This whole thing we can call it a CPU, and then this is the memory in the system, okay. It is, maybe you can call it as a board, a embedded board or a embedded system which has got a SOC with all the pins, and then we have memory. So this is a memory controller actually which has got both address and data bus coming out from the controller, okay. Typically in a system, the DRAM or what we call it as a main memory, okay, it resides outside the SOC, okay. So this is our peripheral, maybe let me draw using a different color. So this is our chip, okay. Now inside that ARM IP is there, and then memory controller. From we, as a system designer, we buy memories, okay. There are different companies manufacturing DRAMs. So the DRAM companies need not be in the same business as processor companies, okay, or they can be the same, but typically there is two different worlds, memory and processor. So this memory we buy, and then the memory controller is integrated into the SOC, okay, and then the programs are accessed from the memory, and maybe we have another memory or maybe a common memory where the core and data is residing based on what kind of architecture we design, and then we execute the whole program. So now going forward for the remaining 3 sections at least, we will 3 or maybe more, almost 6 sections, which will talk about the memory. First 3 sections will talk about cache and memory, okay, which comes in between the processor and memory, okay. There is data cache and instruction cache. We will be talking about it from next session, and then we will talk about how memory is organized and what are virtual memory and physical memory. All those things we will be talking about. So we have completed this. Now before going into the bus, okay, AMBA bus or AHV, all those buses we will be seeing so in the subsequent classes, and then maybe peripherals and how they are connected to a APB bridge, and then on APB bus you may find a lot of peripheral sitting. So we will be covering these buses later on, and then we'll touch upon peripherals and then see how different peripherals connected outside with the chips. Some peripherals may be inside the chip, some may be outside, and then how they are all interfaced. We will talk about those things at the end of the class. So end of the course. So today we will start with memory hierarchy, okay, and then different kinds of memory. Okay, this cache comes inside, and then there are registers inside, and then DRAM comes outside, okay, and then this may be connected to a hard disk, okay. This is hard disk, and then this is the secondary storage. It could be a hard disk or maybe a huge flash memory. We can with the advanced technologies, maybe we will be shifting away from the hard disk and then we will go into a flash memory. So it could be a secondary storage can be called as a flash, or it could also the faster flash can be part of the memory itself. So different levels of memories are there in the system, and we will talk about those things in the subsequent classes, okay. So this is the overview of what we are going to be seeing. So we will not talk anything specific to a controller, because that is very specific to a particular implementation of a controller. So we will only address issues from the programmer perspective, and how does perform, how does the memory perform, and how is it interface with the processor, and what are the different kinds of memories in the system and technologies, and how do they differ from each other, and how does it help us in achieving our system goals. So this is going to be our focus, okay. So let me change over my pen color. Let me take a brown. So in today's class we will talk about memory hierarchy, okay, and then cache memory will be the topic of discussion next, okay. Good. So all of you know, if you are from hardware background, you will know more than what is going to be covered here, okay, and all of you would have heard about this in your earlier classes or courses on digital design, and then we will see how the memory technologies and the CPU technologies are differing in terms of their performance, and then we will talk about why do we need a different kinds of memory to be there in the system, and how do we use them to achieve our performance goal, okay. So effectively everything boils down to performance. What do I mean by performance? Suppose I have built a system, okay, and then is of course embedded system, and then we provide it with some power supply, right, and then we are using this to control something. So some other control system, maybe it could be that embedded system is inside a car, or it could be inside a rocket, or it can be inside a satellite, anywhere. Now how do we define performance? We should be able to make this processor function as long as possible with a limited power. That means what? It should be power efficient, and it should be reliable, okay. I talked about this in the initial classes. So to achieve all this, we have to have not only a knowledge of processor, okay. Processor is one part of it. Maybe I would say it is 60 to 80% of your knowledge, and what you choose as a processor could play a major role, okay. What you write into the processor, the software, but processor as such cannot live alone in a system to realize a embedded system which is performance wise is better, okay, highly performing system. So we need other technologies to be integrated with the processor, like memories, like some peripherals, okay. Peripherals also I can call it as a processor, but if they have a different purpose, and then we will have sensors, temperature sensors, gyroscope, or different light sensor or motion sensor. There are, your typical example is a mobile. So it is not only it has a processor, a mobile, it has got so many things, including where touch screen is a separate system altogether. So knowledge of all these things will make you a complete embedded engineer. So we have now learned quite a lot about ARM architecture in particular, but now we will see how ARM architecture is interfaced with the memory and cache and other technologies. We will be looking at all of them, and that will give you an overview of what an embedded system basically contains. Okay, fine. So let us see why we need some memory hierarchy. Well, we have seen a hierarchy in the system. In your in any company, you will have a CEO, and then we will have vice presidents, then presidents, then directors, then there will be senior leads, and then engineers. There are so many. Okay, there is always some hierarchy in any system that you see, not only in the social world, also in the processor world. Okay, or embedded system world. Okay, so memory as such has a hierarchy similar to a pyramid structure, and we will see why it is needed and how does it help in realizing our goals. Okay, just a brief introduction about memory technologies, because we can talk hours together on this. So our intent is not to go into detail of everything or every detail of this, but this is going to be just an overview introduction, okay, which we are very much bothered about. So random access memory, all of you are aware, okay. So what is the random access memory? Maybe let me tell you. See, memory is a sequential. Some data is stored in a address, right? Maybe if I say it is a 4K kilobyte memory, okay. So immediately it should strike you how many address pins are required, okay. How many are required? See, very simple rule. You don't have to mug up a lot. 1 kilobyte corresponds to 10 bits, okay, address line. So 4 means 2 more you have to add, right? So 12 bit of address line is required, and then maybe this memory could be a data bus of 8 bit wide or 16 bit wide or 32 bit wide, doesn't matter, okay. Based on what is the width of the memory, the data bus bit, maybe it will access 1 byte at a time, access it, to throw it out, or it may access 2 bytes in the sequential address and then puts it on the bus, or it could be 4 bytes in the sequence. So address width decides the size of the memory, all of you are aware, and the data bus width decides how fast in one access how much of data is taken out from the memory, okay. So I am not going into the details of how our address is decoded inside RAS and SAC, all those things we might have already seen in the memory technology. My intent is not to go into those details, but we are going to see a typical memory. Why do we call it as a random access memory? Okay, that only my intent of explaining this was this. So before that, let me go to the another kind of a storage, a secondary storage, a tape. So if suppose all of you are aware of audio tapes, maybe we may not be using it no more now. So the songs are stored in audio tape. Suppose you want to hear the second song, you will do a forwarding button and then you will try to see the second song, right? And if you want to see the fourth or fifth, then you may have to forward it and then see those, hear those songs. This is a typical example of audio tape, okay. Audio tape, I don't want to draw it. So okay, now the tape is also used for a long term storage, okay. For a typical secondary storage, tapes are also used. Hard disk is one which you have seen it and seen it in your systems. So these are sequential accesses, because you can't go to a particular data until you skim through the whole thing. Similarly, in a disk, if you want to seek a particular a sector and a cylinder, then you may have to go to that the particular place and then access them, okay. A tape is an example of a sequential access. Whereas what do we call it, a random access here? That is the time taken to access any part of the memory. Okay, it doesn't matter whether the address is it's at 4 kilobytes. So suppose if I tell some other address, or let me change the color. I want to address for 1 kilobyte. From 1 kilobyte I want to access some 10 bytes. Okay, or I want to access address at 2 kilobyte location and I want to access some 30 bytes. So the address could be varying from 0 to 4 KB, and then I may be interested in accessing any part of that memory. It need not be a 10 byte, it could be a 1 byte in that location also. So when you have a random access memory, the time you take for accessing a particular location is independent, means the access time to get a data value for a particular location, it takes equal amount of time. I am not saying that it is very fast or something, but we compare to sequential access, it is not that if you give me address which is at the 4th kilobyte boundary, it will take more time compared to the first location in the boundary. So it is like equally difficult, or the access time will be independent of the address that you are trying to access. So that's the difference between a sequential access. Okay, and it provides you any address you give, it provides you the data. Okay, with a relative delay, but is independent of the address. So that's what I am calling it as a RAM. So the basic storage units in a RAM is a cell. Okay, 1 bit. Typically DRAMs are done that way. So multiple RAMs form a memory. Okay, this is all some high level which you might have already be aware of. Static RAM is one technology, okay, which is built with purely a transistor circuits. Okay, maybe a 6 transistor. Maybe later technologies which may have a lesser transistor than this, but this is a typical example of a larger footprint. That means if you want to design a SRAM, okay, of a size 4 kilobyte, okay, let me take the same, maybe it may take this much of space, suppose. Then if there is another memory which I will be just going to talk about, DRAM, okay, dynamic random access memory. So this will be much smaller compared to a SRAM design. Okay, why that explanation is coming all the way. So this 6 transistor specs, if you want to etch this transistor in a circuit IC, it will take its own sweet location. So if a particular cell takes this many transistors, then the space area occupied will be larger. So that's one feature of SRAM. I am not calling it as a drawback, but it is a feature. And if you have a transistor of this much, then they will be power hungry also, because transistors will be in 2 states, right? Either it is in a cutoff region or it may be a saturation region, because zeros and ones are defined typically in that location. So it will be consuming a lot of power from the VCC. Okay, so when it is powered, it retains the value. If power goes off, this SRAM is as good as having nothing, and it is relatively insensitive to disturbances, because this transistor circuits, when I say electrical noises, it could be EM, electromagnetic disturbances, okay, which SRAM is not impacted much, and it is very fast in terms of access time compared to DRAM. Okay, and it is expensive because you need a bigger size, because larger footprint, and building that kind of a huge memory in SRAM is a expensive proposition compared to DRAM. I'm not telling that it is compared to something else, but it is compared to DRAM technology. Now what is dynamic RAM? See, both are RAM, random access memories, but this is called static RAM, and this is another technology which is built with a transistor and a capacitor. So it holds a charge in the capacitor, and then we have to, as you know, any capacitor is left, even if you charge it to some queue. If you leave it for some time because of the leakage current, it will discharge slowly, okay, but it will finally get discharged fully after some time. So if you want to hold a 1 or a 0, see typically a memory is used to hold either one of these values. So if you want to hold one of these values, you need to have the charges in the capacitor to be retained. So you need a refresh cycle to make those DRAM cells refreshed frequently so that the value is retained. Suppose if you are holding a 0 in a particular position, accordingly the same value is retained. If suppose a DRAM cell is having a 1, we should keep that continue to have the same value. So don't think that when you are refreshing it all will become 1 or all will become 0. They will continue to be holding the same value, but we need this. So this means a DRAM based on number of bits you have and then the size, there will be a refresh circuitry also required. Even if you have an additional circuitry, the benefit of DRAM in terms of footprint is much better compared to SRAM. Okay. So even you have additional circuitry, that doesn't matter. Actually, the problem with the DRAM is the power consumption, because you are running this. I'm not about power consumption. It is about the having this frequent refresh. Okay, doing that regularly is what is the problem with the DRAM. And another problem is sensitive to disturbances, because it is holding the value as charges. You know that any electromagnetic radiation may induce charges, correct? So they may disturb the bits which are stored in the DRAMs. Okay, so comparatively compared to SRAM and DRAM, what you need to remember is, okay, this for a given size of a memory, okay, maybe our standard size maybe 4 KB. The footprint is the area taken to etch this particular SRAM or a DRAM takes a larger size compared to DRAM, but DRAM has a problem that it has to be refreshed frequently, okay, and then it is much slower than for SRAM. What I mean by slow and fast, it is in terms of access time. So when I give an address to the memory, okay, when the processor, not maybe processor gives an address to the memory, how long does the memory takes? How long does it take to give back the data? Okay, that is access time. So the access time is actually a critical feature, okay, or a parameter which decides what memory to be closer to the processor. Okay, if access time is more, then the processor needs to wait for longer time. Okay, because you know processors are running faster compared to the access time ranges, because from these numbers you can make out. I'm not showing the access time here, only the refresh time. So access times are much lower or higher in terms of time quantity. It is much more bigger value compared to the processor speeds. So if the processor has to get a benefit and then doesn't have to wait for long to get the data from the memory which is having a lower access time should be closer to the processor. Okay, so then naturally you can choose, given an option between this, which one will you choose? I told you the SRAM is faster. SRAM is faster compared to DRAM. So basically, when the CPU is there, the natural tendency is to keep a faster memory close to it. Okay, I will tell you why and know more about it. So that as soon as the address is given, not as soon as, but at least after a less amount of time, the data is back into the CPU. Maybe I can keep a slower guy away from the processor. Okay, so maybe I will access it in advance so that the slower access time can be absorbed. Okay, so suppose if I need a data maybe down the line, I may give the request early so that I get it before, get it in time when the CPU wants. So who is the king here? Who is the CEO of this organization? Our CPU, because what is below them all are slaves. No SRAM or DRAM is all do not have anything. They just do what the CPU is asked to do. I give me the data and then I'll give you the data. So they are all dumb devices, I would say. Whereas CPU is the only, but it is not true with the organization. So I'm not calling that CEO is the only brainy guy and the rest of the organization is not. So please do not relate these two and then tell that this is what I am conveying here. So I am trying to say that organization is like this, but once I come to processor world, please do not associate any other features of this. I'm not saying the CEO is the fastest and then the VPs are slow and then the directors are much more slower than that. Please don't ever think like that. That's not true. If you are so, you cannot go up in the ladder. Okay, so let us only talk about processor now, no longer a social hierarchy. Very good. So I have given you a flavor of memory. Let us go into some more details. So this is the comparison. These numbers may not be exact. It is very close, but okay. So the access time in terms of, see, don't say that 10 is bigger than 1, so access time this is better. Okay. No. If it takes, suppose SRAM takes 1 nanosecond to access the data and give you the data, process the data, and then DRAM takes 10 nanosecond, you can't say DRAM is better than SRAM. Here the guy with a lower number is better, okay, because it is giving me the data much faster. And then refresh is not needed here, but it is needed there in DRAM. It is not noise sensitive, but DRAM is. And cost wise, it is like this. Okay, if this costs $1, okay, maybe a similar size of SRAM will cost you $100. It's only a relative number. No, don't try to go and look at the cost of a DRAM and SRAM and then sue me that it is not in this ratio. Okay, it's only a relative number I'm trying to say. So cache memories and main memories. This we should have a clear idea. I told you SOC. Cache is mostly they are inside. Okay, L1, L2 cache. Some L3 cache or something is nowadays outside. And memory is always, okay, we keep them outside. Okay, so we call it as main memory, which is normally implemented, realized with a DRAM. Okay, so you have a freedom. You can use any kind of memory to store the values, right? You can have a flash, you can have a DRAM, or you can have a ROM. There are so many other things which I am not talking about. You might have E squared ROM, PROM, programmable ROM. There are so many kinds of memories. Okay, we need 10 hours or more to talk about only memories. So I am trying to talk about that in a 1 hour session. So we can't talk about everything in the world. So I have taken only what interests us at this moment. So cache memories are implemented which are inside or with the SRAM technology, and main memories are implemented using DRAM technology. Okay, so that is a typical technology we could do. Okay, there are other flash and other things are there for along with the main memory there may be some memories. Okay, so typically these are the two technologies that are used. Okay, now I explained about memory access is slower. Let me talk about that. So DRAM typically takes this many nanoseconds, whereas and then further systems may need 3x longer or more to get the data. See, actually the access time may be this much, but as I told you, the processor is inside, deep inside. Okay, there is a cache in between, maybe level 1, level 2 caches, and then the DRAM comes outside. Okay, so even though DRAM has access time of this, there is some more delay coming in. Okay, it is for some benefit, but that it is like before you go and meet the company CEO, you may have to go through the security first, and then maybe the divisional secretary, then personal secretary, and then you may have an appointment with the CEO, right? So the data which needs to flow from no, DRAM has to go through different levels of cache, and then it reaches there. But there are advantages. No, you may wonder if this is all causing problem. Remove all of them. Okay, connect CPU directly. No, there is these cases are there for some purpose. I will talk about that in the subsequent lectures. But what I am calling here is some more delay will be there in accessing the data. Whereas the processors are becoming faster and faster. Even our PCs are running at above gigahertz, 2.5 gigahertz, 2 gigahertz, or this kind of a frequency is being used. Processors are used at this clock rate. So this 1 gigahertz converts. If you draw this 1 gigahertz clock, 1 gigahertz will be how much? 1 into 10 power 9, right? Gigahertz. 1 clock cycle will be this much, correct? So this is nothing but 1 nanosecond. So 1 clock cycle, and as I told you, CPUs, processors are designed with a pipeline. So effectively the throughput is okay, 1 instruction getting completed per cycle, CPI, cycles per instruction. Okay, and average it is, we claim that it is a 1 clock cycle. 1 instruction comes out or get executed every clock cycle. That means the processors are now running at this speed. Okay, it is having capability to execute 1 instruction in 1 nanosecond. Okay, but does the memory have that kind of a speed? Unfortunately, they are not. They take 100 times. Maybe it is coming down, but still it is in the range of few tens of nanoseconds it takes to give the memory. So you may wonder, why is it related? Let me tell you. I told you that pipeline is there, instructions are flowing in, and then they are going out. You may wonder, I have an add instruction, I have a move instruction within a register to register. Okay, I have some OR instructions. You have seen lots of arithmetic instructions, and none of them are having anything to do with memory. They are all operating within the registers which are inside the processor. And why are we making so much of fuss about memory? See, any processor, even I told you in the VPU case, any processor, it is not sufficient if it performs some jobs within the registers. They have to come out. It is similar to a restaurant. The cook is making lots of food. Okay, if the food is residing within the kitchen of the restaurant, there is no use of it, right? It should come to the tables, and the guests all the customers should get fed. Then the person in the cash counter will make money. So the processors, if they are executing only instruction within themselves and don't try to interface with the memory or some peripherals, or it doesn't control any other systems outside, then what is the use of the CPU executing at 1 gigahertz and doing something within the register? No use. So finally they have to come out of the world to do something. They need to get some data from outside world, and then they should throw some data out, right? So that time what happens? Memory comes into play. So the number of instructions that is related to memory access, they are much more. Okay, I think it is from 30 to 40%. Okay, if I am right, but it depends on application. You cannot call it as you cannot give a fixed number that this many out of 100 instructions. Okay, I can't confidently say okay, around 60 instructions will be only arithmetic instructions which are operating on registers, and then the remaining maybe 40 instructions will be memory based or memory related. It is very specific in a particular application. So what I'm trying to say is a useful application will need memory accesses also. Okay, so we have to worry about how fast the memory gives us the data. And when I say data, please don't relate only to the data what you get from LDM and STM. Okay, our problem is not only with only these instructions. Okay, so that is one more thing you should keep in mind. Instructions. Okay, I told you, though arithmetic, add or whatever instructions are all arithmetic operation, they can do with only registers inside, so they don't have to come out of the memory. But how did the CPU get this instruction? First of all, it got it from memory only, right? So the instruction access, that is a very important point. Okay, I shouldn't have missed out this, and I don't want to. So instruction access is also a very important part of this. Maybe you may have vector processor where a small instruction does a bigger job inside, that is okay, but even then the data is coming from outside world. So whenever you say data access, we have to keep both these two in mind. Processor to run, it is not sufficient if it operates with registers, but it has to get the instructions on what to do. It is coming from memory. So it is very important that memory interface with the CPU is, and no, the problems with that are well understood, and then it is resolved using some technologies or mix of technologies to achieve our performance goals of embedded systems or any system, I would say. Okay, even your CPU, your PC has to run faster. We need to have all this in mind. So please remember, memory access is not only for data; it is for instruction also. So that is very important point. Okay, so we are talking about load store. So whatever I said was around 30 to 40% turns out to be correct. It is exactly 33%. Okay, as per this particular example. So approximately 1/3 of instructions being loads and stores. Okay, apart from instruction accesses, the memory, the LDM and STM instructions, because we are talking about RISC. So our focus of load store is only two types of instructions are there in the RISC processor which accesses memory. So there is no doubt about those things. So maybe swap is another part of that. Okay, do not worry about that. Don't question me that. Okay, fine. These are all the important points that I wanted to highlight here. Let us go into some interesting facts. So I got it from a paper published, okay, in 1997, not too old. So that's why we have a data. Maybe it's still 10 years back. It's fine. Okay, this graph is not changed much now in 2014. You know, you can extrapolate it and then see that this is growing this way. Okay, maybe this technology might have increased, but the CPU is also increasing. So effectively speaking, the gaps will be there. Okay, so why is this gap building up? The reason being CPU performance increases 60% per year. So this is the kind of advanced processor architecture which we talk about. Parallelism, pipeline is one kind of a parallelism. There are so many scalar processors and then vector processors. There are many more advanced processor architectures. Research is going on in that field. A lot of interesting research going on in this field has made the CPU's performance increase by 60% per year. I'm not saying that memory technology is not increasing, but in particular a DRAM technology, the average increase in performance is 10% per year. It's nothing to do with the lack of research, but it is the limitation of the material used or the system limitations. Okay, so it's not that the research scientists working on this are better than this. Okay, I'm not saying that. So effectively, what is happening? The CPUs are becoming much more powerful. See, it's not only the CPU processor technology, even the processor technology. What I mean processor technology, that is, you might have heard about 32 nanometers, okay, 28 nanometers technology, the chip, okay, when you have a wafer, okay, what is the technology we use to etch the circuitry inside the wafer, okay, that decides how much you can pack into a particular chip. So as you go into the lower technologies, we are able to keep millions of transistors, billions of transistors inside the chip. So a complex circuitry, a complex, not only a single core or even multi-core processors are possible to be built into a single chip. And because of this, the CPU is going up in terms of performance. Processor architecture advancements as well as the technology both aid in improving the performance of the CPUs. So there must be something done to make sure whatever the time amount we spend, money is being spent on improving the performance of CPU is met, and it is not, you know, the CPUs are not made to wait because of memory being slow. Okay, that is very important. We have to keep this CPU engaged with useful work continuously, do something to parallelize the instructions, or do some operations, okay, or keep some temporary storage inside the CPU so that this memory speed is offset. That means it will exist, but still we will achieve the better performance in the CPU. So we are going to see what are the different ways we could do that. Okay, that's our goal of this particular lecture. Okay, now though we are trying to address the problem that the CPUs and memories, okay, interface has, and then we are trying to reduce this gap, okay, in some means, but the program which is running in the CPU, okay, if it is not helping us to achieve this memory latencies to be absorbed, then we cannot do much, okay. But luckily, to our surprise, the programs that are running in CPU, okay, they have a principle of locality which helps us in our goals, okay. Let me tell you what is that. Program tends to reuse data and instructions that are closer to those they have been recently or that were recently referenced themselves. What I am saying is CPU is here, memory is here, okay. Let me draw it to scale because memory is going to be occupying more space compared to the chip inside, okay. We are accessing a particular part of instruction, and then the program is also accessing some part of the data, okay. And then let me not leave out our friend stack, okay. Now let me explain to you. Suppose you are, I hope you are familiar with a simple C function. So you are calling a C function, okay, with some parameter float A, okay. So sorry, B. So you are declaring int I, maybe I declare some 100, okay. Sorry about the handwriting. I should tell this in every lecture. So by now you are used to my handwriting. So thanks to you. Thanks for your patience. Now assume, don't tell me why are you declaring a huge array inside. What are you going to do? I will do something. Okay, don't worry about that. So some code is running, and then you will say return maybe k. Some local variable is declared as k. Let me return it. So let me say this function is returning a integer. So what is happening? This is some main function. Okay, I am calling it with a value 2 and then 10.5. I can do this. Preferably this customer, this compiler converts it to integer format, and this is type. This is the 10.5 floating point. I can, instead of passing a variable, I am passing some values to the function. Okay, something is being done. Now I am saying this is having a principle of locality. Let me prove it. Okay, assume this has got a some small for loop. Okay, and then it is operating on this register, this array, and doing some computation. Some maybe floating point is coming, so some mathematical computation, some sign or cos or whatever you want to do. Okay, so effectively assume this is having some 5 instructions. Okay, in terms of C, so maybe if it is converted into some assembly, it could map onto some 100 assembly instruction. Roughly. Okay, the whole of the for loop. Okay, now what happens in the memory? Let me go to different color. I am getting bored with this color, so let me erase this guy. Okay, this actually will justify why I am saying the locality of reference is very important. That's why I am taking some time. Memory is there. Let me use different colors for different kinds of data. So I said stack. Okay, our friend stack. Where is this I is there? I is located. Our I is here. Okay, assume that 100 integers are stored in this array, and then let me take it is using some global variable. Okay, global variable, maybe it is using some global array also. Okay, int g. Okay, it is supposed to be g, some 100 assume. Okay, some global variable. A strict programmer will say that accessing a global variable, an array of global variable inside a function is not partitioned. It is not right current of programming. So please ignore those comments for a moment. So it is accessing a global variable also for some purpose. Where are they? They are in some data. Imagine both are in the DRAM. Data is here. Okay, it is in some other part of the data. Now let me draw some other. Maybe I pick up green. For a moment, let me say that maybe a flash, you are accessing the instruction from flash directly. If that is the true, or that is the case, instruction is here. Now what all different kinds of data, and okay, thing I have told you, this is there, this is there, this. Now the principle of locality, is it true for all, whether accessing this or this or this, is it true? Take this example. I of 100 is all accessed within this array. Within maybe if it's 4 bytes it takes. Okay, given the size of this to be our friend 4004 KB, right? This 4 bytes into 100 is how much? What, 400 bytes, right? It's a smaller percentage of that. So that much of memory is accessed, assuming some huge caches are there. Okay, now this program, whatever I written, is concentrating on a small portion of the memory inside this program. Agree? Do you agree? And then it is also accessing another array of data which is in another part of the memory, but that is also 400 bytes. Okay, and what about instruction? I told you instructions is of how many instructions? Where is that? I said 100 instructions. The whole for loop is 100 instructions. So there are 100 instructions compared to maybe the size of this flash, maybe it could be 2 KB or whatever. Relatively, I will say that instruction size is supposed to be lower than the data size, the DRAM size. So a small portion of the code is accessed, because finally this instruction whatever we wrote is converted into assembly and stored there in the instruction. So instructions are also having a principle of locality. That means what? The program whatever we write, okay, tend to reuse a data and instruction. It is reusing because it is for loop, right? It will go back to the same starting of the for loop. So it is accessing this set of instruction more, 100 times it is accessing. So if suppose if I tell you I have a method of, okay, let me come back to some addresses, some method of keeping this instruction, the set of 100 instructions close to the memory, close to the processor, and then maybe out of 400, maybe if I can accommodate everything into a data cache, okay, assume that there is a temporary memory available within the CPU. CPU is a processor with some cache and some memory controller, some small peripherals, all that, okay. So if I keep all these instructions and the data inside the CPU, don't you think I can do this job much faster, because I am going to use SRAM here, okay. I will use SRAM technology to build this cache. I told you that in the previous slide. So I am not going to use DRAM, what I used in building this main memory. So what happens? This will provide me data much faster rate, and then I have enough space to keep all those instructions that are used recently. Both instructions and data I am keeping it close to the CPU, so I can do much faster. Okay, it is similar to, okay, I hope you got this. Locality of reference is there in both that data access in as well as in local variables or stack, and then in terms of instruction everywhere. Because of this program is structured like this, I can have those things which I need very close, so that I can perform my job much faster. So CPU is able to accomplish its goals, though it is running at under sub nanosecond speed, it can perform the job. So there are two kinds of locality. Temporal locality. Temporal means time. Recently referenced items are referenced in the near future. So a for loop comes back after some time, right? Similarly, arrays are also accessed if they are closer data. That is spatial locality. Suppose if I have an array of 100, most probably a computation involving this array will be using the elements one after the other within that space. So that is called spatial locality. That means the data which is kept in the memory, which are close to each other, are used by the program more frequently compared to some other data here, some other data somewhere else. Okay, I am not claiming that it will use only the data which is closer. It may pick something else. Otherwise, you can't achieve. You can't write a meaningful program. But the percentage of using a closer data is more, much more. Okay, please understand that. So spatial is in terms of location in the memory, and temporal means in terms of time, because when I have a for loop, that instructions are going to be executed one after the other in the time sequence. Okay, so in terms of time also they are going to be accessed very frequently. So this is a quiz time now. Take 2 minutes. I don't think you need more. You have to tell whether each of this, okay, particular thing correspond to whether it's spatial locality or temporal locality. Okay, just write it in a piece of paper. Don't look at the neighbor's paper, of course. Okay, it doesn't matter even if you get it wrong. Nothing. Okay, take a break. Okay, welcome back. So array elements, I think mostly I have given these answers in my discussion itself. So correct, array elements are closer in memory, so spatial locality. Access of sum of each iteration. See, which sum? I am not talking about this sum. It is not inside the iteration. Maybe I should have resolved this. Inside this for loop there is a sum. This is a variable. Okay, it's a one single variable sitting somewhere. It is not close to this array A. Okay, that's why I told you. Data elements need not be accessed which are very close. They are also accessed, and some variable which is sitting somewhere. Maybe it could be a global because you are returning. So it is not a global variable. Maybe it's a local variable, but it may be after some local variable it will be in the memory. So is some accessed because of being closer to A, or is it because of some other reason? It is because it is inside the for loop, correct? So naturally anything to do with the for loop is because of the time, because after some time the for loop is going to be repeating. How many times? N number of times. Okay, sorry, I gave this result. By now you may have the result. So instructions are accessed inside in a sequence. Please remember the pipelining itself, instruction pipelining architecture. Okay, instruction pipeline basically depends on this particular case. Okay, the instructions are all accessed from the subsequent addresses. So it is a spatial locality, and always normally jumps or say sequence of instructions are executed and jump is taken, and then another sequence and then another jump. So this way it goes. The jumps are not frequent. Okay, it may be 30 to 40% again. Okay, the number of jumps that you see may be once in 4 to 5 instruction they say. Okay, number of jumps in a instruction stream, 5 sequential instructions will be executed maybe after one jump instruction may be encountered. Because if you don't have this ratio, then there is no point in having a pipelining structure itself. So there is an inherent benefit of executing instructions in a sequence before you encounter branch. Then you go and then start executing another set of instructions. So instructions in a sequence is a spatial locality. Okay, it's very obvious. Cycling through the loop is temporal locality. Okay, so I hope these are all clear to you. Okay, let us go. Memory hierarchy. Before we come to memory hierarchy, I think you are now convinced that it is required. I think we can go faster in the remaining cycle. Let us see some fundamental of enduring properties of hardware and software. Fast storage technologies cost more. Okay, it is like in our Indian IPL team. Okay, the person who scores more run rate. Okay, in a cricket match, the person who is holding a maximum run rate will cost more in the auction also. Correct? Cost is more based on the speed. So memory with a fast technologies, that means the access time is much lower. They cost more to implement, to build. So and moreover, I told you that this gap is also widening. Okay, and well written programs tend to exhibit good propriety of reference. This is one benefit which we got. Okay, we didn't do anything particular for this, but the programs are such that they always need which are very close to each other, which are accessed very frequently. So we have this advantage and we have some disadvantage. Because of this, we are going to marry these two to our advantage. Okay, the fundamental properties of complement each other, that's a beauty. Okay, so if you put these two together, then we get a better performance. So they suggest an approach of organizing memory such as a memory and storage systems known as memory hierarchy to achieve higher performance. Okay, so it gives us a reason for doing this. Now this is the hierarchy I have shown you. Processor is sitting inside. Okay, CPU registers, or you can call it as CPU here, the head of all. So these are the memories. Okay, the guy who is in the top is closer to the CPU. Okay, and then we have memory which is further a little bit, and then DRAM is outside the chip and disk may be outside the system. as the memory goes away from the CPU, okay, as you can see the width is increasing. Okay, pyramid will be stable when the width is increasing. So the storage space increases. Okay, this is the size of the memory. You might have heard, nowadays terabytes of disk, gigabytes of RAM. Okay, MB of megabytes of cache. Okay, those days are gone where these were all reverse. Okay, terabytes of disk, gigabytes of DRAM, megabytes of maybe it is not too long, but they lie between these two. Okay, maybe still the caches are in kilobytes also. Okay, maybe if you see the embedded word, so maybe I may swap these two, or I will keep these two together here. So kilobytes of cache and few registers. Few means maybe 32 registers to 128 or maybe more. This is the size of memory you have. So that's why the pyramid is going this way. Other way I would have put it this way. Okay, let me explain. Smaller memories are faster but expensive. Okay, I'm not striking it, I'm trying to underline it. Larger memories are slower but cheaper. Okay, that's the way it is. SRAMs are costlier, but you can't keep too much of SRAM memory inside the chip. So you tend to keep, because 6 registers I told you, right? So and they consume more power. So and L2 cache also of this type. DRAM here, this is the main memory. So you have more expensive which are closer to this, our CPU. Okay, exploit locality to get the best of both worlds. What I am saying is, since our programs are having a beautiful property called locality of reference, why don't we make use of it? So because of that, what happens is, because the program running in the CPU are going to access more frequently the memory or data or instruction which are in the cache compared to what is in the main memory, you get the best of both worlds. Most accesses are to the faster memory. Okay, and larger memory available with the cost cheaper. But can you do away with, can I say that, okay, anyway most of the accesses are to the local memory, I don't need DRAM at all, disk at all, I will keep only the cache and then build my system? It is not possible. Your program, what I told you is, a smaller part of the memory is used more frequently. That doesn't mean that your program is small. Your program is a larger one. Nowadays kernel is coming into going up to few megabytes kernel size. Forget about your program, application program occupying few megabytes. So your program is larger, but at a time you may need a smaller part of the program, and then you may go to another part of the program based on the input or based on the control flow of the program. So you need this larger memory, but you need the smaller memory which are faster to improve the performance. So based on this, what are you trying to achieve? We achieve the most of the memory accesses of the CPU. Okay, since they are happening, they are only to the local memory, that means the faster memory. So most of the memory accesses are faster. That means we have a faster memory from the CPU perspective. Okay, but I am able to keep a larger program also, and I am able to run this larger program also with this hierarchy. So the amount of money that as a program developer or as a system builder I am going to spend on storing this program in a memory, maybe a disk or a flash, is lesser, cheaper. So larger programs are saved or preserved or maintained in the system using a smaller memory or a cheaper memory, sorry, and execution is happening with a faster and a costlier memory, but it is small. Based on this, we get the best of both worlds. That's all. Okay, I hope I don't have to reiterate this and all of you are convinced about it. Now this is a kind of a detailed structure. Okay, if you want to go into the details of each of them, please freeze this and then see, but most of the things I have already told you, and these are all L1 L2 caches or different layers of caches. Don't worry about this if you don't understand, we will talk about it in the subsequent class. Okay, now another quiz for your, okay good, I don't want to do one more mouse click, take maybe 5 minutes. Okay, you need to have, for each of this you need to have either this or this. Okay, which is larger or smaller, don't put equal to. Okay, I am not talking about this condition at all. So you need to fill for each of the comparisons one of this. Take 5 minutes break, come back. Okay, welcome. What is access time? I explained you multiple times. Which is faster? SRAM is faster or DRAM is faster in terms of access? Please remember access time in absolute value. Okay, suppose if I call SRAM's access time is TS, and if I call access time of DRAM is TD, which will have a smaller value, correct? So you have to be careful. Don't say that, oh, SRAM is much faster, so no, must be okay. I'm sorry, one more thing I need to tell you, I is closer to processor and I than I plus 1. I forgot to mention. I hope while taking a break you might have noticed this notes. So if you don't, if you are not done, please, because this is closer to the memory, sorry, CPU, and this is farther from the CPU. All these elements are for the memory which is farther from the CPU, and this is for the closer to the CPU. That you should know. Okay, I is this, I plus 1 is below. Okay, maybe I plus 2 is below. So maybe if you understood in a reverse way, you might have got all of them in a different way, but that doesn't matter as long as your understanding is good, that's fine. Okay, cost you must be knowing, I already told you. The memory which is closer to the CPU is expensive. Memory size, you can't keep too much of memory closer to the CPU because of so your SoC cannot be room size, right? It needs to be fitting within a board or small chip. And transfer bandwidth, that is a speed with which how many, see, it's not even speed, it is how much of data is, see, bandwidth is something which you should all know. You might have heard about LAN, right? 100 Mbps. Okay, those are old days. Okay, uh, 1 Gbps. What does it mean? 2 Gbps, whatever. This is how many bytes. If I put a watch, a stopwatch, and then look at, okay, I stop it at this time, T0 and T1. Okay, this is the LAN cable or a fiber cable. Okay, I look at this, how many bytes get transferred in a given time. That's what is called bandwidth. Okay, so CPU is sitting here, and a cache is here, and some disk is here. So how much of data you transfer between each layer? That is what is called transfer bandwidth. Okay, and how fast you do. Okay, so since you are accessing cache quite often, that transfer bandwidth is higher than the other ones, because other memories are going to give you data in a very lower rate. But this is very important, unit of transfer, how much of data you take, okay, from CPU to cache. This is like this, how much you transfer. It is maybe if I can explain you one thing. You might have heard about Walmart or Food World or some stores. They have shops here. They have a storeroom there. Okay, storage space. Okay, and they have multiple layers. Okay, in the Bangalore or any other city, they may have a storehouse, and then they may have a different at a higher level, maybe in Delhi or closer to the port. They may have a bigger storehouse. So when they are bringing items into the stores, Food World or Walmart or whatever stores, what happens? They access initially, some maybe few packets of or few bunches of being data, a particular not a data, sorry, some items from this storeroom. But when they are getting it from another intercity or intracity, they don't transfer one packet of data, right? One packet of items, biscuits. They may one carton of or multiple cartons of data or items they ship in that range. So as they go farther and farther from the stores, the amount of items that are transferred are becoming bigger and bigger, because the transport cost is equivalent to how much you transfer. Actually, if you add more, it's not going to add more, but if you are adding more trips, it is going to cost you more. So as you go away from the place, you tend to get more amount of items or more amount of things in a one transfer. That's the normal logic. So unit of transfer very close to CPUs are in terms of bytes, whereas between a disk and DRAM it may be in terms of kilobytes or megabytes. So as you go further, the amount of unit of transfer will increase. That is very important. Okay, if you apply a natural logical thinking, if you do, you will be able to relate this and then get convinced about why it is happening. And the frequency of access, how frequently you will be getting the items from another city, maybe once in a month, maybe within a city once in a week, but maybe from the local stores every day. So the frequency of access for a store as the distance increases is becoming more. That means you will do more frequently here compared to what you do from the farther distances. Okay, I told you this is one month, once in a month, this may be once in a week, and you are storing it once in a day, because items are getting over, then maybe in a day itself they will be supplementing it some more items in the store. So effectively what is happening, the frequency in terms of number is more for the memory which are closer, or the system which is closer to the consumption. So it is equivalent to a CPU consuming the data, where the stores people come in and then consume the items. It is closer in a CPU world or in our programming world. The data is consumed by the CPU, so it accesses more frequently the memory which is closer compared to the farther one. So it actually gels well with the reality. Very good. So there are three important properties. Inclusion, any data part of the lower level. So what I mean by lower level is actually in the figure it is higher level, but which is closer to the CPU. I told you I, farther is I plus 1. So this is lower in terms of index at least. Okay, so this is the lower level. So inclusion, that means what? Any data which is here as well as which is here. I would say any data here will also be here, and if it is here, this will also be here. I'll take an example. Suppose you are accessing a file which is in the disk, correct? The file is accessed by the OS code running in the DRAM, main memory, and then maybe a small one page of that is brought into the main memory, so it is here, and then maybe a particular block of that data is going to the cache, so it is here, and then maybe one data element, maybe an integer value, is going into a register. Now is this data element which is accessed and put into the register, is it here in the file? Of course, if it is a data file, suppose, okay, your program is accessing the data, maybe it is an image okay, JPEG image, you are converting into some other format. So every pixel has to be in a file, which is stored in a file, needs to be coming to a processor. You agree? It could be a CPU or it could be maybe a coprocessor. If it is a image processing, maybe our friend VSP will be accessing that. It doesn't matter. As long as I am, when I say CPU, please remember it doesn't matter whether it is a VSP or a floating point processor or somebody else. They are all same processor. Okay. So a small data in the file has to come to the register here to get operated. That means to get converted. It may come to a floating point processor or it could come to a CPU register, but they have to come. But while coming, they come to DRAM and they come to cache and then to the CPU. That means the data what you see here in the CPU is there in every level. You agree? Okay. This is, I have convinced you that any data in the file has to be here and it should be there in every place. But you may ask me another question. Suppose if I have an instruction called add R1, R2, R3, maybe the data what I have I is here. I am intermediate addition I am doing and putting it in R1, which is not there in the file. Okay, intermediate results which you encounter in registers need not be in the final file. Okay, so that's one caveat which you should keep in mind. Okay, but I have convinced you that the data in the file has to be in all the levels before they come into CPU. So that is also true, and this is also true. This is maybe the percentage will be lesser than what you normally see here. That's why the inclusion is true for everything except for registers. Okay, otherwise every memory level below they have to have an inclusion property. Coherence. What is the coherence? Multiple copies of the same data are available at each level. See, when I copied a thing back to CPU, I kept a copy everywhere on the way. But suppose if I am modifying it and I want this to be also modified, suppose maybe this file is being sent in real time by converting from JPEG to another format. Okay, assume JPEG to some other format you are transferring, and then it is sent to our network to some other player who is playing maybe JPEG or MPEG, it doesn't matter. Okay, movie MPEG form, and we are converting into another video format and sending it. What happens? A MPEG file is coming into CPU, then it goes into another format, goes into it doesn't go into immediately, it goes into different stages and then goes into a file and then getting sent over network. That means any data that is there should also be in every other places also. Okay, they need to have coherence. It's not that you have some other data here and something else on this side. Then there won't be correctness of program. So coherence is another property which you should all keep in mind, and if you can relate it with the real application, it will make sense. And locality of reference I have talked about so many times, so now by now you are all familiar, so I don't want to talk this here. So okay, so these are the different three properties in memory hierarchy. Okay, let me pictorially show a virtual memory. I have not talked about this. This will be coming soon. So now you assume it's a huge memory compared to physical memory. This is our main memory, and we copy what is required from file. This may be a file system disk. Okay, we copy what is required, and then we split it into blocks. Okay, each page. This is page, and they are split into blocks and going into the cache. Cache is some other SRAM, a faster memory inside the CPU. Okay, CPU is here. Okay, now it is multiple words are copied. These are all words. Words may be based on the CPU. If it is a ARM processor, our friend, so it is a 4-byte word. Okay, byte, not bit. Let me complete it. So now what happens? Those bytes, whatever is required, is copied into the register. So let me explain again. Suppose a particular value I told you some JPEG or MPEG, some pixel data is required, which happens to be a floating point value or maybe an integer. It is required in a register. what you need to do? You need to copy maybe a particular the file may be of big size. Okay, one movie may be few megabytes or whatever size. So you may copy few kilobytes, okay, into physical memory, and then we copy few 32 bytes or 64 bytes or 128 bytes we copy, and then finally out of which we copy one of them. So this I, if it is here, we don't take. Okay, I showed you this way. So let me assume that I is here. We will not only take I from here. I told you that when we are taking it from farther, we need to get a larger value blocks. It's like a store here. The food world or Walmart is here, and they are accessing it a small item that they will not take only one item. They take one carton of item, right? So it comes here. A few kilobits come, out of which I am interested in only one packets or something. So I take one small portion of it, and that, so I is lying here, suppose. Then I will come here and sit somewhere. Okay, I assume that it is here. Then it comes finally here. So that's how the memory is accessed. So this is very frequent. This is little bit more frequent, and this is the every instruction maybe. Okay, so you get the benefit of memory hierarchy here. Okay, so this is a huge data table, but I don't want you to mug up this. Okay, have an idea. Okay, how it scales in terms of latency, how different memories scale, and then where these memories are physically present in the system. You know that, let me start from register. It is in CPU registers. Okay, it is in the CPU. It may be a 32-bit word. TLB, I will talk about it later. It's something to do with the virtual memory management. So ignore it now. Cache is few kilobyte, okay, of size, but one block is of 32 byte. See, cache size itself will be kilobyte, but one block will be of 32 byte. So multiple blocks will be there in a cache. So cache can be either inside a chip or out of chip. Normally L1, nowadays L2 also inside the chip. Second two levels, but as you go further, the cache size is increasing. See here, the virtual memory pages are increasing, and then these are all in megabytes and kind of increase in size. These are all something to do with the networking and the web-based technology, if you are aware of. So web pages, when you are accessing it, it comes from the web cache. Web cache is like a proxy server. Actually, if you are accessing a Cricinfo or anything, which is Cricinfo is feeding cricket scores live. They will not have a one single web storage, in a sense web server feeding all over the world. You know that there are people accessing this cricket info when the match is going on from all over the world. So they will keep multiple proxy servers which will feed based on the location. Suppose from India there may be some few cities. They know that the traffic is more from IT world, because people working in IT companies watch those cricket info more frequently than a guy working on the road or a civil engineer doing some constructions. So naturally, IT Silicon Valley will have more accesses to the Cricinfo during the office hours than other places, right? So Cricinfo will see the traffic on the network and then put the proxy servers, that means closer to the places where the access is more frequent. So the web cache is of that kind. So that gives the data, and then it comes to your web browser cache. And when you switch over your web pages based on your manager is nearby or not, then it will be caching different kinds of pages on the browser, and finally it comes into our network, and then when it has to be displayed on the screen, it has to go to the GPU, the graphic processor unit. Okay, that means it has to go through the buffer cache. This is the cache which is used for buffering the data access from the disk, and then it goes to virtual memory, and then maybe cache, and then finally the processor displays it in the screen. So your data, Cricinfo data, finally gets to your screen through passing through all these stages. Okay, so that's the way things are done. So who is managing them? The different kinds of no web browser or a OS or maybe a hardware, and then who is deciding which pixel to go where, and the assembly who is writing. It could be an assembler generating a code, or it no actually managed by this, but actually developed by you and me, right? You are writing the program, okay, and managed by you are not deciding that my variable I should go into register R0 or it should go to the register R1. You are not deciding, right? When you are writing a program, maybe if you are writing an assembly code as a programmer, you will be deciding that my particular data should go into a particular register. Otherwise, it is done by the tool if it is a high level language. So this is what is a comprehensive comparison of different memories. So I thought I will give you a flavor of where the virtual memory system is all about, but don't worry if you don't understand this. I will be talking about this now in the subsequent lectures. So processor is here, and then there are TLBs here and cache, and then main memory comes, and then disk. So DMA is a direct memory access. This will be performing a transfer of data without involving a processor to access data from the disk to the main memory. Okay, so this is a typical system, and cache will be accessed by the memory directly, both for data and instruction. That is very important. Okay, so with this we have come to a end of the class. Okay, so I hope this was very useful to you. Just to give you an overview of how a memory technology plays a role in our processor architecture. So what you write in your code actually, okay, assembly code, what you write, you need to keep in mind what is the cache block size, okay, what is the page size. If I tell you this, you may not believe that, but actually if you design your program, your data structures, keeping these in mind, actually you will be improving the performance of the system. So to be a successful programmer, successful system engineer, you should not restrict to only one part of the world. You should know about everything around this memory and how they relate to your program. So that holistic view will give you a better understanding of how to optimize your program and how to get a better performance in your system. Okay, so it doesn't stop it only the processor. It even involves networking. Okay, so I'm not telling that you should know everything, but you should have an idea of all of them to have a better understanding and to design a better system in the to achieve the performance goals of the system. Okay, so I really enjoyed sharing this with you, and see you in the next section for taking a journey through different caches. Okay, cache means not this. Okay, if you understand this cache, you will get better cache. Okay, have a nice day, enjoy your day. Thank you very much. Bye bye.